So far we've been working with derivatives this whole course, and now we are going to jump into another main topic in calculus, which are antiderivatives or integrals. So let's talk about this, and I'm trying to find my pen. There it is. So basically, it's the reverse of differentiation. I'm trying to find something that if I took the derivative of what I found, I get back the function. So let's kind of read through this. Let's think about it and come up with some formulas. So let me just read through at this point. Gosh. So at this point, we know how to find the derivative of various functions. We know now asked the opposite question. Given the function f, how can we find that function with the derivative of f? If we can find the function capital F, the derivative of f. So we can call capital F the antiderivative of f. So again, a function capital F is an antiderivative of a function little f if we take the derivative of this antiderivative and we get our original function for all x in the domain of f. Okay, so we're thinking backwards. So let's say we had some function f of x equals, and then we're going to start using 2x. So think about it for a second. Can you think of what you can take the derivative of and get back 2x? So the antiderivative of 2x is going to equal x squared, right? And we can check this by taking the derivative of this. If I take the derivative of x squared, right, I bring my power down front, subtract 1 from my exponent, and I get 2x. But what about, could capital F of x equal x squared plus 1? If we took the derivative of this, right, derivative of x squared is 2x, and the derivative of a constant, 1, gives us back 0. So that also works. Well, then doesn't that mean that I could add any constant to this? Because I know that if I take the derivative of any constant, then I get back 0. So this could technically be x squared plus c, where c is equal to a constant. So taking the derivative of this, I get back 2x plus 0. Well, let's think about it. Why is that? Well, let's think about again what a derivative is. When we take a derivative, we're looking at the slope, right, of that function. Well, if we look at this parabola, which is x squared, and I took the derivative, let's say, let me pause the video for a second so I can grab this and copy it. Okay, so again, if we take the derivative, that's telling us the slope of our function. And in this case, it's x squared. And so let's say I wanted to find the slope right here, let's say at A. And so I would go up to my graph and I would find a tangent line, the slope of the tangent line there. Well, recall if you had some function and you add a constant to it, all that's doing is it's shifting our function either up or down. It's a horizontal or a vertical shift. Let me just paste. So if I take this function, it's growing at the same rate, it's just shifted up. Or it could be shifted down. Let's do it right here. So if I look at this at x equals a, and I go up above, oops, okay. And right here, I could see that that's going to be the same slope at x equals a. Which is the same slope down here at x equals a. And so these are all have the same slope. That constant doesn't affect it. So that's kind of the reasoning behind why we can add that constant c in there. Okay, so let's think about maybe a different example where we're trying to find the antiderivative. So maybe we have f of x is equal to x cubed, and we're trying to find what we can take the derivative of to get x cubed. So remember, when we take the derivative, we subtract, we bring down our power, and then we subtract one. So we know that when we have the antiderivative, when we take the derivative of that antiderivative, we have to subtract one from our exponent, and we want to get an x cubed. So we need to start with a fourth power. The problem is, if we think about this again, when we take the derivative of this x to the fourth, we're bringing that exponent down front. So that would give me 4x cubed, but I want 1x cubed for my function. And so how we can compensate for that is we can divide by our new power. And so let's divide this x to the fourth by 4. And then let's add some constant c. And so if we check, we can show that the derivative of our antiderivative, which is capital F, is going to give us back our original function, little f of x, which is x cubed. So bring our power down front, we get 4x, subtract 1 from our power, we get 3. That's all over our new power 4. Derivative of a constant is 0. Our 4's cancel, and we're left with, this is x cubed, which is equal to the original. So it works. So notice we added 1 to our exponent and we divided by our new exponent. And so that actually brings us to the general power rule. Before we do that, let me just talk about this a little bit. So let capital F be an antiderivative of little f on some interval I, then 1 for each constant c, the function capital F of x plus c is also a derivative of little f over that interval I, which we were just talking about, and I showed you geometrically why. 2, if g is an antiderivative of little f over I, there's a constant c for which capital G of x, the antiderivative of g of x, equals capital F of x, which is the antiderivative of f of x plus c over I. In other words, the most general form of an antiderivative of f over I is the antiderivative of f of x plus c. So notice that we have capital letters. We use capital letters to denote it's the antiderivative. So if our function is little f of x, we would denote the antiderivative of that little f of x as capital F of x. If our function was given up to us as little g of x, we would denote the antiderivative with capital G of x. Guess I don't have it in here. So we have a rule. If f of x is equal to x raised to the nth power, we have to have one little stipulation on here that n cannot equal -1, and we'll talk about that in a second. Then the antiderivative, which is capital F of x, this is going to equal, add 1 from our exponent, so we're going to get an n plus 1 power, and divide by our new exponent, n plus 1, plus some constant c. So here's our rule finding antiderivatives when it's a power function like this. Again, we can check. If we took the antiderivative of this x to the n plus 1 all over n plus 1 plus c, bring down our power down front, we have n plus 1. Subtract 1 from our exponent. That was all over n plus 1. Derivative of constant is 0. So simplify, our n plus 1's cancel. And this is x raised to the n plus 1 minus 1 power. So the 1's cancel, and we're just left with x to the n, which was our original. So for sometimes right now when you're first figuring out that antiderivative, you might want to test it, take the derivative of it, and make sure that you got back the original function. Okay, well, this could get tedious to keep on saying that we'll find the antiderivative of this. There was different notation when we were looking at finding derivatives, right? If it said find the derivative of f of x, there was different ways that we could denote that we were taking the derivative of f of x. We could denote it with that f prime of x. We can denote it with df over dx. There was other ways to do it. Well, same thing with antiderivatives. There's a way that we can denote that we're taking the antiderivative of a function. And that is with what is called indefinite integrals. So just pull this up bigger. So notice you have this kind of elongated S symbol right here. So this elongated S symbol, it's called the integral sign. And the integral of f of x dx is called the indefinite integral of f. We'll be talking about definite integrals next week and the difference between what an indefinite and definite integral are. But right now we're just going to deal with indefinite integrals. So given a function of f, the indefinite integral of f is equal to the integral of f of x dx is the most general antiderivative of f. If capital F is the antiderivative of little f, then we can say that the integral of f of x dx is equal to capital F of x plus c, the antiderivative of f of x plus c. The expression f of x is called our integrand. And the variable x is the variable of integration. So this kind of dx, this tells us what we're integrating with respect to. So if I saw a dt there, that would be telling me I'm taking the antiderivative with respect to t. So let's look at some examples. And then we'll get into finding the antiderivative of other functions other than our variable raised to a number. Well, let's just start easy. What if we had the integral of 6? And let's say that this said dk. So this is telling me I'm integrating 6 and my variable is with respect to k. So again, we're thinking backwards. What could we take the derivative of to get 6? Well, if I had 6k and I took the derivative of that, that would give me, with respect to k, that would give me 6. So that's good. And then I'm going to add my constant c here. So if we had, let's say, the integral of just 2x plus 3 dx. So antiderivatives work similarly to derivatives. So remember, if we had multiple terms that we were summing together, we could take the derivative of each term and sum that. And so same idea here. So let's look at the first 2x, and we're thinking to ourselves, what can I take the derivative of to get back 2x? Well, if I use that general power rule, which says I have the integral of x to the n dx, all I'm going to do is add 1 to my exponent, divide by that new exponent, and add c. So if I think about it like that, that coefficient in front too, I'm going to ignore. I'm just going to bring it down. And now let's use that rule. So this exponent's not shown as 1. So if we add 1 to our exponent and divide by our new exponent, plus, so taking the antiderivative of 3, well, I need an x there in order to take the derivative of it just to get back 3. And then I always, when I'm dealing with indefinite integrals, I'm going to add on this constant c. So we found that the antiderivative, or the integral of 2x plus 3, is equal to 2x squared all over 2 plus 3x plus c, which reduces to x squared plus 3x plus c. Check it really quick. Derivative of x squared is 2x, which we get. Derivative of 3x is 3, which we get. And the derivative of a constant is 0. So pulling up another one. What about the integral of the square root of z dz? So recall when we were taking and just learning how to take the derivative, and we were learning those new rules after we did the limits. we had to rewrite our derivatives, our function, before we took the derivative sometimes. So same sort of idea here. Let's first rewrite this so it doesn't have the radical. And we can rewrite the square root of z as z to the 1/2 power dz. So if we use our new rule that says, when we take the antiderivative, we're going to add 1 to our exponent. So 1/2 plus 1. I'm going to write my 1, though, to have a common denominator, 2 over 2. We're going to divide by our new exponent. And then we're going to add some constant c. So let's just simplify this a little bit. So this is z to the 1/2 plus 2/2 is 3/2 divided by 3/2 plus c. Well, we don't really like fractions within fractions. So this is the same thing as z to the 3/2 times the reciprocal of this denominator. Reciprocal is 2/3 plus c. I would probably rewrite this just because this started with a radical. So I would probably rewrite my 3/2 power as a radical. And then I would bring my coefficient, that 2/3, in front of that radical. So this is equal to 2 all over 3. And z to the 3/2 power, this is the square root of z cubed plus c. So questions on that? So part of the exam, I might say, find the antiderivative for one part, and the second part I might say, now show me that what you found as the antiderivative is correct. And so you would show me that by showing that the derivative of what you had is 2/3 square root of z cubed plus c. The derivative of that gives me back my integrand, which in our case is the square root of z. So let's just check real quick. Actually, before we check, we want to keep the antiderivative in the form where it doesn't have the radical. So it's 2/3 z to the 3/2 power plus c. So now taking the derivative, we have that 2/3, bring down our exponent of 3/2, subtract 1 from that exponent. 3/2 minus 2/2 is 1/2. Derivative of a constant is 0. 2/3 times 3/2 cancels, and z to the 1/2 can be rewritten as the square root of c, which again is equal to our integrand, which is, and I should have called this f of z, not f of x, because our variable was z, not x. Okay, so next example is the integral of 1 over x cubed dx. So again, this is in a form that we don't know how to take the antiderivative of, but we can rewrite it so that we know what the antiderivative is. So let's rewrite it so that we don't have x cubed in the denominator. We can rewrite it by bringing it up into the numerator and changing the sign of the exponent. So this is equivalent to x to the -3rd power dx. Now we can use that general power rule where we're adding 1 to our exponent and dividing by our new exponent. So adding 1 to -3 gives us -2. So we got x to the -2 power, all divided by -2 plus c. Oops. And I probably would rewrite that without a negative exponent. So the antiderivative is -1/2x squared plus c. So what about the antiderivative or the integral of 1/x dx? Recall, there was a stipulation for the integral of x to the nth power dx. Your exponent couldn't equal -1. And if I rewrote this 1/x, that would be x to the -1 power. So that general power rule is not going to work here. You guys remember what you took the derivative of and got back 1/x? Recall taking the derivative of the natural log of x. I'm going to put absolute values here because if x has to be greater than 0 in order for you to be able to take the natural log. And then plus c. Derivative of natural log of x is 1x, 1/x, which is this. What about the integral of e to the x dx? What did you take the derivative of that got back e to the x? We'll recall the derivative of e to the x was e to the x. So the antiderivative of e to the x is e to the x dx. Oops, not dx, sorry, plus c. Okay, well, sometimes it wasn't just e to the x. Maybe it was e raised to some coefficient times x. So let's look at what we'd have to do in that case. What if it was e to the kx dx, where k is equal to some constant? Okay, so remember, taking the derivative of e, it's itself, that e function itself, times the derivative of the exponent. So we have to keep that in mind when we're taking the antiderivative, because when we take the derivative of that exponent, in this case, we would have k in front of our e, and we don't want that. So if we look at the original itself, and instead dividing by that coefficient in front of the x, k plus c. So now let's check it. When I take the derivative of e, it's itself times the derivative of the exponent, which is k, all over this k. Derivative of c is 0. K's cancel, and we're left with e to the kx, which is our integrand, and so this works. Okay. We came up with a new rule to help us. Here's the other rule that we just did. The antiderivative of 1 over x is the natural log of x plus c. So there were a couple other rules. When we took the derivative of an exponential, but the base was not e. So let me just give you these. So if a is greater than 0 and a is not equal to 1, then the antiderivative or integral of a raised to the x power dx, this is a to the x, all divided by the natural log of a plus c. Recall, if we had a to the x power and we took the derivative of that, this was equal to the original function times the natural log of our base. So that's why we have to divide by this, so that when we do take the derivative, it cancels out. What if that coefficient wasn't just x, 1x, it was a raised to the k times x dx? Well, remember, we would have to look at the derivative of the exponent. So we have to deal with that, divide by that k, and the natural log of a plus c. So now we have an example where we're taking the antiderivative of x squared all times the quantity x to the fourth plus 4x plus 3, and that quantity, and then dx. So just like when we were taking derivatives, and we didn't learn the rule yet of the product rule, we manipulated it first so that we could take the derivative. Same sort of idea here. We don't know how to take the antiderivative of this product, but we could distribute first and then take the antiderivative. And so we would have the integral of x squared times x to the fourth gives me x to the sixth, plus x squared times 4 to the x is 4x cubed, plus 3 times x squared is 3x squared dx. Okay, so taking the antiderivative of x to the sixth, we're going to add 1 to the exponent, so we get 7, divide by our new exponent of 7, plus the antiderivative of 4x cubed, keep the 4, leave it alone, and now antiderivative of x cubed, so add 1 to our exponent, which is a 4, divide by our new exponent of 4, plus 3, add 1 to our exponent of x squared, so we get x cubed, divide by our new power of 3, plus c. So let's just simplify this. We have x to the 7th over 7, plus, well, 4's cancel over here, so just x to the 4th, plus these 3's cancel here, so just x cubed, plus c. What about the integral of 1 minus 2 cubed root of x. And this is all over the cubed root of x dx. Say, okay, so again, this is not in a form that we know how to take the antiderivative of, but we can manipulate this. Notice in this quotient that our denominator is just one term. So we can rewrite this so that we're just dividing each term in the numerator by the term in the denominator. So we could rewrite this as 1 over the cubed root of x plus, or actually minus 2 cubed root of x all over the cubed root of x dx. So the cubed root of x is x to the 1/3. So 1 over x to the 1/3 is the same thing as x raised to the negative 1/3 minus 2. And notice that now we can cancel these cubed root of x. So we just have that minus 2. And then all of that dx. So we've manipulated it to a form that we can now take the antiderivative. So the antiderivative of x to the negative 1/3, add 1 to our exponent. So negative 1/3 plus 3/3 is 2/3. All divided by our new exponent, 2/3, minus 2. And to get derivative of just negative 2 back, this has to be negative 2x plus c. Rewrite this. So this is 3 x to the 2/3. I'm going to rewrite that as the cubed root of x squared. I'm flipping this 2/3 up so that this will be all times 3/2 minus 2x plus c. Let's take a break and then we'll come back, do a couple more, and then I'll give you some tricks on what to do if even we don't see how to manipulate it, which is using substitution.